Welcome to Naradar Academy. In this video, we are going to discuss about linear transformations on non-linear spaces and also about conjugate space. Let's start with linear transformations. See, let n and n dash be non-linear spaces and t be a linear transformation from n into n dash. Then the following conditions are equivalent to one another. See, already we have seen what is meant by a norm-linear space. Norm-linear space is a linear space in which we are defined with a norm which satisfies certain conditions, isn't it? So here we are taking two norm-linear spaces n and n dash, and we are defining one linear transformation from n to n into n dash. The following four conditions are given here. That is, all the four conditions are equivalent to each other. That is, if one is true, then two is also true. One is true if and only if two is true, if and only if three is true, if and only if four is true. Okay, right? What is the first result? T is continuous. That is, the linear transformation is continuous. That implies that is true if and only if T is continuous at the origin. That means whenever you take a sequence xn converging to 0, then the image T of xn, that sequence should also converge to 0. This is called what? Continuity at origin. So the transformation is continuous if and only if the transformation is continuous at the origin. Right? And this is true if and only if this condition, third condition, is satisfied. So what is the third condition? See, there exists a real number k such that norm t of x is less than or equal to k times norm x for every x belong to n. Okay, that is this. Look at this. Look at this property here. Here, what do we say? Norm t of x is always less than or equal to k times norm x. That means this k can be considered as bound for the bound. Okay, it can be considered as an upper bound for this linear transformation, right? So from this, what can we conclude? T is continuous if and only if it is bounded. Okay, so all the four conditions are equivalent to each other. No, from the third condition, what do we conclude? T is continuous if and only if T is bounded by some k, and this k is called bound for the transformation. What is the final condition? The set of all unit sphere, that is, set of all x for which norm x less than or equal to 1. That means what? Closed unit sphere in n. That is, set of all points inside and on the closed unit sphere. If S is like this, then its image T of S will be there. No, T of S, the image of the unit sphere in n dash, it has to be what? Bounded. Right? So all the four conditions are equivalent to each other. So this is the first result. Next one. See, k defined in 3. That in third one, we have defined k value. No, that k is called what? Bound for linear transformation, and t is bounded if and only if it is continuous. So this is a deduction from the previous theorem only. Next one. How to define norm of a linear transformation? See, if t is a linear transformation from n into n dash, then norm of the linear transformation is defined to be norm t is equal to supremum of norm t of x such that norm x is less than or equal to 1. That means if you want to find what is the norm of the transformation, collect the values of all t of x for which norm x is what? Less than or equal to 1, and you take the supremum value. That value will give you the norm of t. Okay, if your norm linear space n is a non-zero norm linear space, in that case this definition reduced like this. That is, norm t is equal to supremum of norm t of x such that norm x is always equal to 1. Okay, so this is the norm defined on the set of all linear transformations from n to n dash. There is another way of defining norm t, that is infimum of. Already I have told you, no, a transformation is continuous if and only if it is bounded. So bounded means what? It will be having bounds, upper bounds. So norm t is again defined using the bounds. Norm t is equal to infimum of all k, where norm t of x is less than or equal to k norm x. That is, collect all the values of k for which this equation is satisfied. Okay, for all the values of k, you find the infimum. That will also give you a norm. So this is one norm and this is another norm. Another way of defining norm of linear transformation. So from this what can we conclude? Norm t of x is always less than or equal to norm t into norm x. Okay, right. Next one, the set of all bounds, that is the set of all k's are there, no, equal to the set of all equal to the set of all radius of closed spheres center at origin which contains t of s. The next one, so we have started with set of all linear that is linear transformation from a norm linear space n into n dash. We may have so many linear transformations from n into n dash. That collection is there, no, that is represented by script b of n n dash. This denotes the set of all continuous linear transformation from n into n dash. So we are going to discuss some special properties of this b of n to n dash. So for this set we have defined already norm here. So definitely this is going to be a norm linear space. If n and n dash are norm linear space, then the set b of n n dash will become a norm linear space with respect to the norm defined above. Okay, and this can also be a Banach space. Banach space means what? Complete norm linear space. When will this become a Banach space? Only when n dash is a Banach space, right? Okay, then the next one is here randomly we have taken what? Two norm linear spaces n and n dash. Suppose if we are considering continuous linear transformation from a norm linear space n into itself, okay, that is denoted by b of n. Instead of writing it as b of n comma n, simply we write b of n, and those transformations are called operators on n. Okay, so operator means nothing but continuous linear transformation or from a norm linear space into itself. Okay, and this b of n is an algebra. Okay, now let n and n dash be norm linear spaces. Then what do you mean by isometric isomorphism? Isomorphism means it has to be bijection and it has to be a linear transformation. That we know. What do you mean by isometric isomorphism? Isometric means norm t of x equal to norm x for every x belong to n. Okay, so that is called what? Isometric isomorphism. Next one is we are going to define what's a conjugate space of n. See, the set of all continuous linear transformations from a norm linear space n into either the set of complex numbers c or from a norm linear space n to set of real numbers, that operators, okay, that linear transformation, that collection is called what? Conjugate space of n, and it is denoted by n star. And the norm value is defined like this: norm f is equal to supremum of modulus f of x. Why do we put modulus here? Because from one norm linear space to either the field of complex numbers or the field of real numbers we are defining, no. So norm is nothing but modulus only. Either we can define supremum with this or with infimum like this. This n star is a Banach space. Next few results we want to discuss. LPn star. Star means what? What I told you, conjugate space. The conjugate space of LPn is equal to LQn. What is this P and Q? P and Q are numbers greater than 1 and less than infinity with 1 by P plus 1 by Q equal to 1. And conjugate space of L1n equal to L infinity n, and conjugate space of LP equal to LQ, and conjugate space of L1 equal to L infinity. Okay, and but conjugate space of L infinity is not equal to L1, and C naught, conjugate space of C naught equal to L1, and conjugate space of capital LP equal to capital LQ. This capital LP is nothing but Banach space of all measurable functions f defined on x, okay, for which modulus f of x to the power p is integrable. Okay, that's all. Thank you.